In this video, we shall look at the photoelectric effect. As the name suggests, photo refers to light, and electric refers to electricity. The phenomenon known as the photoelectric effect occurs when light incident on certain metallic surfaces cause the emission of electrons from these surfaces. These emitted electrons are known as photoelectrons. Let's see how this works. Assume you have a metallic surface, like that. It could be sodium or aluminum or say silver. Now let's assume we shine light on this metallic surface, like that. It's a monochromatic light with, let's say, frequency F. Let's look at the cross-sectional view of this metallic surface, like that. Right on the surface of this metal, there are electrons, and these electrons are bound in the metal. They are bounded there by a surface potential energy barrier. This beam of light that is hitting the metallic surface consists of small bundles of energy called quanta or photons. Let's imagine them to be like that. Each would carry an energy equivalent to the Planck constant times the frequency. A photon arriving at the surface of the conductor is absorbed by an electron. That electron. The energy transfer in that process is an all or nothing process, meaning the electron gets all the photon's energy or none at all. If this energy is greater than the surface potential energy barrier, which traps the electron can escape from the surface, like that, creating electric current. This surface potential energy barrier has a name. It's called the work function, which can be denoted like that. So the production of these electric current by the incident light is what is known as the photoelectric effect. Let's look at this one-to-one process. The electron that is released from the surface of the metal would have a certain kinetic energy. The maximum kinetic energy for an emitted electron is the energy gained from the absorbed photon HF minus the work function of the metal, which can be thought of as the surface potential energy barrier that must be overcome by this electron before it can get released. So we can write the maximum kinetic energy of the electron equals the energy absorbed from the photon minus the work function of that metal. We note that the unit that we use to quantify work function is either joules or electron volts. We see that in order for this to happen, the frequency of this light must be greater than some minimum value, known as the threshold frequency or cutoff frequency. And this cutoff frequency is dictated by the material that is being illuminated, because each material have their own work function. For example, for aluminum, the work function is 4.3 electron volts. For sodium, the work function is about 2.7 electron volts, and so on. So work function is instrumental in determining the cutoff frequency. How do we determine the maximum kinetic energy of the electrons? To do that, let's introduce another metal here, and let's introduce a potential difference between this metal and the metallic surface. Let's call that potential difference V. If we provide negative charge to this metal and make the metallic surface, say, positive, that would create an electric field in that direction. An electron, being negatively charged, that is getting released with this much kinetic energy would obviously slow down by this electric field. And we can change this potential difference until it gets to certain value, let's call it V sub s, where none of these electrons would reach this negatively charged conductor. When that happens, we can immediately write the maximum kinetic energy as quite simply being the electric potential energy, namely the electric charge times that potential V sub s. And this is called the stopping potential. So by measuring the stopping potential, we can calculate the maximum kinetic energy of these electrons, because we know the value of E, which is about 1.602 times 10 to the power minus 19 coulomb. So you see, this formula can also be written as E times the stopping potential equals the energy absorbed from the photon minus the work function of the metal. Now let's plot the value of the electric current produced by these photoelectrons versus the values of the backward potential. So this is the current and this is the values of backward potential until you get to the stopping potential. Of course, when there is no backward potential, the current is maximum due to maximum kinetic energy of the photoelectrons. As you increase the value of the backward potential, like that, you see the current would drop all the way until it hits the zero mark. And this is the magnitude or the value of the stopping potential, minus to show that we are dealing with a backward potential. Forward potential exists when the rod is positively charged and the metallic surface is negatively charged, in a case of which the electric field would go that way and that would naturally accelerate the electrons. So in this diagram, the current would just saturate up to a maximum value for a given intensity of light. Each frequency or light with each frequency would have its own curve. If, let's say, you have another light with the same intensity but with a different frequency, let's say a frequency that is less than that, its graph would look something like that. If you assume the new frequency is f2 and f2 is less than f, then this stopping potential for the new light with the same intensity, by the way, would be minus V as, let's call it 2. The value of the stopping potential increases linearly with frequency of the light used, because in photoelectric effect, the frequency of light used dictates the energy of the electron released, and intensity of light used dictates the number of electrons that are released. We note here that the purple graph levels exactly at the same current value as the green graph, because in both cases the intensities of light used are the same. Now let's look at a problem. A sodium surface is illuminated with a light of wavelength 0.32 micrometer. The work function for sodium is 2.7 electron volts. Calculate the energy of each photon in electron volts. Well, that is simple. The energy of photon is given by the Planck's constant times the frequency of the radiation. And since frequency equals speed of light over the wavelength, the energy can be calculated like that in a unit of joules. So H is 6.626 times 10 to the power minus 34. C is 3 times 10 to the power 8 meter per second. The wavelength is given 0.32 micrometer, so in meter it's times 10 to the power minus 6, which is 6.21 times 10 to the power minus 19 joules, or in the unit of electron volts, it's 3.88 electron volts. Now how do you get from here to here? By dividing with the charge of the electron, which is 1.602 times 10 to the power minus 19 coulomb. Part B. What is the maximum kinetic energy of the ejected photoelectrons? The maximum kinetic energy is given by the energy from the photon minus the work function. HF was found to be 3.88 electron volts. Work function is 2.7 for sodium, and that's going to give you 1.18 electron volts for the maximum kinetic energy. Part C, what is the cutoff frequency for sodium? Now we know from this equation, the photoelectric equation that is, the maximum kinetic energy equals HF minus work function. So when frequency equals the cutoff frequency, then the kinetic energy goes to 0. That means the cutoff frequency, F sub c, equals the work function over the Planck constant. So first, let's calculate the work function in joules. So it's 2.7 electron volt. If you want to calculate that in joules, you simply multiply with the charge of the electron, like that, and then to that you divide by the Planck's constant, which is 6.626 times 10 to the power minus 34. And that will give you the cutoff frequency in hertz, namely 6.52 times 10 to the power 14 hertz. Finally, what is the stopping potential for the setup? We know the stopping potential is given by E times the stopping potential equivalent to K max. So the stopping potential is K max in joules, so 1.18 times 1.602 times 10 to the power minus 19, that is to convert electron volt to joules, divided by the charge of the electron, which is 1.602 times 10 to the power minus 19 coulomb. So that goes away and it gives you 1.18 volts for the stopping potential. And that solves the problem. Thank you for watching.